Hello, everyone. I'm Jin-Sheng from Zhang University. Today, I'm excited to present scaling multi-agent path planning with GPU from computation success to future vision. Our talk will cover a brief introduction, detail our work, discuss our future vision, and conclusion. In multi-agent system of computation, we focus on two core components: task scheduling, deciding which robots to which task, and path planning, figuring out how they get their result conditions. The primary challenge in real-time decision. This demands fast dynamic task assignment. Faster is critical due to the massive search space. When the number of tasks is 1.5 times the number of agents, the planning window is more than 5, and we have no more than 10,000 agents. This formula underscores the sheer scale of possibility the LMAPF planner might consider versus the assignment itself, emphasizing the need for a faster assignment to fit into already complex planning phase. Dynamic is also important, as new tasks appear and the old ones are completed, requiring constant re-evaluation. Along this, we need an effective LMAPF system to maximize task completion. Our motivation is twofold. For faster dynamic task assignment, we aim to leverage GPU acceleration, triggering reassignment whenever new tasks are reviewed. For effective LMAPF, we draw inspiration from the winning solution of the 2023 legal for robot runners, as detailed in the paper below. To understand our approach, it's crucial to briefly touch upon the difference between CPUs and GPUs. CPUs typically have 10 cores, are optimized for low latency and serial operations, and process complex control logic. GPUs, in contrast, boast thousands of cores, are built for high throughput and parallel operations, and excel at high computations per memory access. This difference are key how we can accelerate our algorithm. Let's dive into our work. Starting with processing. A key step is calculating the heuristic maps, which we do using GPU. To calculate it, we start from the target location and expand outwards. This process is generally faster due to the GPU's parallel processing capabilities, which allow for simultaneous calculations across many map nodes. Furthermore, our heuristic calculation incorporates the cost of rotation, providing a more realistic path cost estimation for agents. Table 2 clearly demonstrates the performance benefits of using the GPU for heuristic map computation. You will notice that for larger, more open maps like warehouse, Paris, and sortation, the GPU provides a significant speed up over 7 to 9 times faster than a 64-core CPU. This is because the GPU can process the heuristic calculations for tens of thousands nodes in parallel, which is ideal this expensive environment. Interestingly, for the BRC 202D game map, despite having a large number of free nodes, the speed up is more modest at 2.53 times. We attribute this to the map's structure, which is characterized by numerous narrow corridors and passages. These features can limit the breadth of parallel expansion during the heuristic calculation, thereby reducing the GPU's ability to fully leverage its massive parallelism at each step of the computation. I know that most methods calculate the heuristic map in advance and then upload it to the server. We use our GPU method for time considerations. For example, The heuristic map of sortation is 6 GB after compression. Assuming the upload speed is 20 MB per second, it will take more than 5 minutes. But our methods only takes about 90 seconds. Next, task schedule. Based on the heuristic map calculated in the processing phase, we can calculate the cost of each agent to complete each task like shown in the table. Our task schedule have 5 steps. Transfer agents location and task locations to GPU memories. Calculate pair cost of agents and task on GPU. Flatten the valid pair cost. Sort flatten the pair cost with GPU. And finally assign tasks to the agents in descending order of the cost. Noted if the agent is moving towards the first arrow, the agent and the task are still in an assigned state. Dynamic reassignment is crucial. For example, as shown in the diagram on the right, after A1 completes T2, if T4 remains assigned to A4, a newly revealed T6 might inefficiently be assigned to A1. A dynamic system would evaluate potentially assign T6 to A4, thus improving overall efficiency. This is why we trigger reassignment when new tasks appear. For path planning, we adopted the windowed parallel PIBTLNS methodology, which was very effective in the competition. This established approach includes windowed planning, similar to HCR planning for limited horizon, and initial solution with priority inheritance with backtracking, and the refinement with MAPF large neighborhood search. Groups of agents are selected asynchronously, and path replanning for each group occurs in parallel. The algorithm reuses parts of previously planned and refined paths as a hit for PIBT in the next iteration. Looking ahead, our future vision heavily involves CPU. Current MAPF bottlenecks at conflict detection. GPU can check numerous agent pairs and evaluate revolution strategies simultaneously. Instead of replace classic algorithms, we can supercharge them by accelerating demanding parts like parallelizing node expansion and managing large data structures on GPU. The expanded impact is a significant speed up, enabling real-time solutions for much larger agents teams. Inclusion. Our work centers on GPU class acceleration for KLMAPF components. For processing, calculate GPU accelerated heuristic map with rotation cost. Faster dynamic task assignment utilizing GPU for rapid sorting of pair costs to efficiently assign tasks. Triggering dynamically as new tasks are revealed. Path planning adopted the best solution of League of Robot Runners 2023. Our future vision with GPU focus on massively parallel conflict resolution and hybrid MAPF approaches to future enhance performance and scalability. These GPU-centric strategies are key to advancing MAPF capabilities. Thank you for your attention. I would be happy to answer any questions. And you can also reach me at the email address.
Thank you, Jin-Sheng. It's a question from the participants.
May I ask a question here?
Yes, please.
So first of all, thanks, Jin-Sheng, for this, I think, wonderful talk. It's very interesting to sort of apply GPU to sort of traditionally, like CPU-intensive work. I think the first question I have is that from your intuition, because here, when we do the sort of a parallelization, in GPU, there is usually a sort of a point is whether, the task is memory bandwidth limited or computational bandwidth limited. From your understanding here, is the task here is more like memory bandwidth limited? Because, it's like retrieve the distance and then sort of compare the distance.
Uh, uh, in our methods, we should transfer agent's location and the task location to GPU first and
Right.
calculate the cost.
Right.
Yes, yeah, and
Yeah, sorry. The reason I'm asking this is because like for example, when you use GPU for like LLM sort of inference time, and people want to do batch, the reason of doing batch is because it can kind of surpass the memory bandwidth limit. Because computation bandwidth is usually 100 times more than the memory bandwidth. And I'm wondering kind of like the similar phenomenon, does it exist here in the sense of like, is it the memory bandwidth limited or computational bandwidth limited? Does that make sense to you?
uh, uh, you mean our methods is limited by the transfer limitation or the computation limitation? Is
Exactly.
that right? Uh,
Exactly.
uh, in the practice, we saw that uh, uh, such as in warehouse environment, it's just take uh, maybe 100 milliseconds to process these methods. So I think
Mhm.
uh, the competition, the computation uh, um, is faster than the transfer data from GPU to CPU. So the limitation is the on the
The
transfer
memory transfer.
process.
Okay.
Yes, yes.
Gotcha. Thanks. And just a second, a very quick question is that did you implement everything using just like C and the CUDA kernel, or you implement with some other language?
With CUDA C++.
Gotcha. Yeah. Okay. Sorry. The reason I'm asking is because do you find that there's overhead of kind of doing the implementation? Because my sense is that for other people to use this and to improve it, there is a barrier of kind of learning how CUDA kernel works.
Yes, it takes a lot of time to learn it.
Have you thought about sort of using things like JAX or like Traden,
Not
sort of a
not
more
yet.
like? Hmm. Okay.
Not yet. I heard that CUDA is support for Python. Maybe it's easier to learn.
Right. Okay.
Yeah.
Yeah. I feel the same way. Maybe that will be an interesting direction to explore. But thanks overall. This is
Oh,
very interesting.
okay. Thank you for your questions.
We also have a question from the chat. Is how was the vectorization done to solve CBS conflict checks on GPU?
Uh, we are working on it because we found that computation process is hard to be parallelized, uh, such as the time sequence and the agent sequence. So we found it's easier to use GPU to accelerate some components of traditional CBS methods, such as its lower level search, um, uh, uh, so, like A star or others. Uh, did I answer your question?
So Bob, did that answer your question? So we have a follow-up from Bob is how is a data model represented on GPU for CBS?
I didn't get it. What your mean? Data model is do you mean data structure or something?
Yes.
Okay. Uh, uh, mm, uh, first of all, data structure in GPU, such as CUDA, is not uh, 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 mm,
I think one point probably Bob is confused is because actually in GPU you don't have to vectorize in order to get a speed up. GPU is more flexible than kind of usually people think about in terms of you have to do vectorization. It's more like you can actually code like in a flexible way to use whatever data structure if you can make the CUDA kernel works. Is that kind of understanding correct, Jin-Sheng?
uh, yes. In GPU, just uh, set data like uh, array, data array. So there are no vectors data structure in CUDA.
Okay. So I think because we run out of time, and if you have any further questions, just like we can follow up in chat.